Welcome to OPC UA for flat glass industries. It's the OPC 40301. And like already mentioned, I'm very happy that we have these three speakers. So we have Gerald Fehringer, Markus Scheuswohl, and Gesine Bergmann. And I would be very pleased if everybody of you could introduce yourself to our listeners.
All right. Thank you, Heiko. My name is Gerald Fehringer. Welcome to this presentation. I'm working for the company Leisec, situated in Austria for more than 25 years now. And there I have a position as a system architect for our software landscape. And we at Leisec, we are providing machines as well as software components to our customers. And we are in need of interacting with the machines with a lot of different software vendors. On the other hand, with our software with a different number of machinery vendors, and as such we are very interested in the interoperability, and this is why you see me sitting here basically in the first place. And secondly, I'm very pleased to be the chairman of this joint working group, and I have taken over this position recently from Markus, and I would like to hand over to Markus to introduce himself.
Thank you. Yeah, my name is complicated, so just call me Markus. I am a consultant for digitalization and have a long-standing background in the glass industry with reputed machinery builders and software suppliers. Yes, I was one of the founding members. We initiated this group. Later on, you will hear a little bit the history. That's what I will evoke on. And then I'm very happy that Gerald has taken over, and he will then detail more what's happens recently. And all of that would not be possible if we would not have kind of a good soul and a good spirit that keeps us all together, organizes all the events, and always pushes us also to work heavily on the specifications and all its derivatives. And this is where I'd like to hand over to Gesine.
Thank you very much, Markus, and all the team. So now I can skip my introduction a little bit. I'm responsible within the VDMA for everything regarding the foreign glass technology since 2017. And a part of this is also the administrative responsibility for this group. I will also start with the presentation here today. And at first, I will give you a brief overview of what you can expect in the next 45 minutes. For those of you who are not familiar with the flat glass processing, I will give a brief introduction into the products and the processing and the reasons for the standardization. Then Markus Scheuswohl will introduce you to the history of the specification and guide you to the second version of our companion specification. And he will later on hand over to Gerald Fehringer, who introduces you into the job target definition. But let's start with flat glass processing. So flat glass itself plays really an indispensable role in today's life, underpinning functionality, aesthetics of numerous structures and products. You know it from residential homes to commercial buildings, from vehicles to electronic devices. And you may realize that flat glass enhances safety, energy efficiency, and also user experience. And I will give you some examples, starting here with an insulating glass unit. Insulating glass is really pivotal in improving energy efficiency in buildings. This kind of glass provides thermal insulation superior compared to single glass paints, and furthermore also helps in soundproofing. The second picture already shown is an example for safety glass. This is the kind of glass that reduces the risk of injury upon breakage. There are two different types available, laminated glass and tempered glass. So for laminated glass, the fragments stick and adhere to the interlayer, preventing sharp pieces from causing harm. And this is what you can very often find in skylights and windshields and also storefronts. The picture here on the slide shows a tempered glass. This is a glass that shatters into blunt pieces rather than into sharp shards. And tempered glass is also used in application where safety and strength are critical. And maybe you realized it in an automotive side window or also for interior doors. I have a third example here for you. This is a coated glass. And coated glass, this is a glass that features a thin layer of metal or metal oxide at one surface or two surfaces. And this really enhances the performance of the glass. Imagine if you have a low emissivity coating on the glass, for instance, that reflects the infrared light, that makes sure that you can keep the heat inside the room during winter and outside during summer. So coated glass is really crucial for energy efficient buildings today and also for visually appealing buildings. Another very important product here is fire resistant glass. This is designed to withstand really high temperatures and maintain the integrity of the structure, providing really a crucial safety barrier in case of a fire. So there are also various types. One prevents the passage of flames and smoke only. Another one also blocks the heat transfer. And this is also a very important building block for building construction, securing escape routes and make sure that you can evacuate people during emergencies. The very last example given here is a printed glass. So decorative patterns or designs through digital printing or screen printing are applied here. So this is really to add an aesthetic value additional to a functional property. It's commonly used in interiors. Maybe you realize that as a kitchen back wall. So this type of glass really allows architects and designers to create unique visual effects and also offers branding opportunities. There were only some examples, but I think also these examples already show that flat glass and also the derivatives of flat glass really play a fundamental role in modern living. For creating these products, of course, various processes are necessary, and we can only point to some of them. First of all, the cutting table, because cutting is the initial step in the glass processing, where stock plates with a size of 6 to 3 meters are cut into pieces. This involves the scoring of the surface with a diamond or a carbide wheel at first, and then snapping it along the scored line. Or you can also use a laser and a thermal shock for cracking, or even water jet cutting is used. Important is the precision here, because this is crucial to minimize waste at the one hand side and also to ensure that the pieces of glass are cut into the right required dimensions. Following the cutting process is the edge processing to make the edges smooth. This step can involve several steps like grinding, polishing, or beveling. And with this kind, what kind and quality of edge here is made really depends on the application of the glass and the final product. And you should also keep in mind that this edge processing also increases the level of safety for the handling procedure throughout the lifetime of the glass. Another example is drilling. This is also necessary in glass processing if you want to produce glass railings, for example, or facade installations. And this can be done mechanically, as here shown on the picture, or also by laser. Now the machinery starts to become a little bit more complicated. Another example is tempering. That's a heat treatment process to increase the strength and the safety of the glass. So the glass is heated up to a higher temperature and then rapidly cooled. And this process induces a compressive stress on the surfaces and a tensile stress in the core, making the glass much stronger and causing it to break into the small blunt pieces that you already saw. The laminating process. That's a process where you have to bond at least 2 layers of glass with an interlayer made of PVB, for instance, or EVA. The lamination process starts with washing, then placing the interlayer in between, following by heating and the pressing, and finally ending in an autoclave. Last but not least, the lines are becoming even longer as an assembling unit for the production of insulated glass that you have seen on the very first slide. So assembling really means a combination of at least 2 or more glass panes with spacer in the ceiling, and finally create a unit. This is filled with an insulating gas or air gas mixture in the space between the panes. There are some more processing steps available. So each step is really necessary and has really to be taken into account quality-wise for the production of high-level quality products of flat glass. So why is it now necessary to introduce OPC UA into the flat glass processing? Flat glass processing companies are grappling with numerous challenges. And first of all, very often we have the challenge that we have an order size of 1, that complicates the production process. And that also means that the machines have to handle really a variety of glass types and also glass thicknesses, but every time with the same high precision. So automation and efficiency in the production process is really critical to meet the tight deadlines. A second challenge is that today customers have really high quality demands and they can easily detect defects in the glass product. So we also need an advanced quality control feature to ensure that we deliver defect-free glass products. Then we have the challenge that very often the companies are small or medium-sized companies, and they are very often also serving local customers, and this is intensifying the competition. Yeah, the energy-intensive nature of glass production already poses challenges on the whole industry with the rising energy cost. And the energy efficiency of the machines is also becoming increasingly important to control the production cost. And altogether leads to still slim, low profit margins due to the high level of competition and due to the production cost already in the process before. If you have a look at this production site overview, you might now get an idea of the possible complexity of a glass processing company. And with this, you can maybe a little bit understand why implementing OPC UA interfaces is really essential. And I will only mention 2 or 3 several key reasons. First of all is interoperability. Because OPC UA is an open standard enabling seamless communication between diverse devices, regardless of the manufacturer. And in flat glass processing, you can see we have various machines from cutting, processing, tempering from different vendors. So by standardizing communication protocols, OPC UA really allows the integration of the equipment from different manufacturers to facilitate a cohesive and also efficient production line. Second point is also data acquisition and monitoring. So one of the advantages is the ability of OPC UA to facilitate real-time data. In flat glass processing, we need lots of different data from numerous parameters such as temperatures, processing times, pressures, and OPC UA enables the collection of the data from various sensors and machines, providing really a comprehensive visibility into the process. This all leads to enhanced automation and control. OPC UA supports automation by allowing different systems to communicate and to coordinate the actions. And in flat glass processing, automation is really crucial to maintain a high throughput and a precision. I think there's no need to talk about scalability, flexibility, security here, because these aspects were already covered in the talks given before. With this, I start to hand over smoothly to the next speaker, allowing you here to have a brief look at the members of our group. Here you can find companies supporting us in the past and now from both sides meaning the machine manufacturers on the one hand, and also the glass processors as the customers on the other hand. As the flat glass sector continues to innovate and also needs to innovate, the adoption of OPC interfaces will be really a cornerstone in achieving more integrated and intelligent manufacturing environments. Now I'd like to hand over to Markus Scheuswohl, who will give you the deep dive into the content of the companion specification.
Basically, I'd like to start as one of the founding members of the OPC UA for flat glass specification with a history. And it all started in 2019 when we came together, and it was about 10 specialists of machine builders and software vendors in the flat glass industry that sat together and thought about how can we improve our performance with respect to our customers. And indeed, it was obvious and rapidly clear that most we can gain if we have a perfect performance while commissioning our machines and software. And that means that this shall be in a smooth way and the most efficient as possible, meaning that we have to have interfaces that are not proprietary, creating risk and creating also downtimes, but having something that is standardized. Thinking of the topics that have to be communicated, we thought that basically there are three needs for a machine that are required in order to communicate. And this is, on the one hand, it is who am I? That means a machine can identify itself. The second is, what do I have to do? And the third hand basically is then, how did I perform? And if you think about it, it's nothing else than if you set into a new department or a new organization, it's the main requirements that you have. So you can consider a machine as something empathic. And at that time, we were thinking, okay, what helps us now to convey and standardize this message? And as there was already OPC UA standardization ongoing, we verified whether OPC UA can help us. Not only stopping there, we thought, okay, what of the three aspects, identification, jobs, and feedback, is of the most importance? And it was clear that the highest need is with respect to job sending and status, for which we created a job model. I'll detail a little bit later, but we found out that we have to coordinate, to integrate also additional systems. Like example, we have to define a common coordinate system to which we will all adhere. That resulted in our first specification, the 40301, we were very proud of, and we were so proud that we thought, how can we then also communicate it to the glass world? And there was a perfect occasion in 22 when there was the biggest trade fair in flat glass in Düsseldorf, the Glass Tech, for which we made a new UMATI demonstrator where everybody could play with. Big advantage of this demonstrator was that from that moment on, we had a lot of people asking for standards like that to be implemented within the projects. However, it was clear to us that the job sending and status is not the only thing we shall focus on, as here we talk more about metadata. Why we talk about metadata? Because, as Gesine explained already, there are plural ways of manufacturing, milling and drilling of the glass itself, and therefore we need also a little bit more detailed specification. And this is exactly what Gerald will refer to when he talks about the specification of the job target definition. Now, having set up all of that, our third target was then to get also then the feedback of the machine and the production, something others started in the beginning with when they started with OPC UA. And we started to work in our group, and I'd like to show later on how we managed to integrate early with machinery and how we could also, how to say, put a little bit of footprint of the glass industry into the machinery. And we were very happy to work with this one together with Wolfgang Mahnke and with Heiko Hörden, both present today. So coming back, how it all developed. So first we had our specification for job sending and status, and we thought, you know, the world of flat glass is so complex. Let's be happy if we can have a solution that fits already for us. And this is exactly the context, and that was the mindset, how we developed our first specification. Also creating a job model, a state machine model that was particular for the glass industry, certainly derived from other job specifications, together with Sebastian Friedl, who did an excellent job. And we thought, hang on, this is great. This is already working. But we were in the bubble of the flat glass. However, our job specification was such a success with us that Heiko came across, and he thought, hey, I need some new ways of working, or I need some new specifications to work on. And this is how we decided that the job specification of the glass can be one of the major starting points to create the job specification for machinery. But certainly, I mean, that is not something that the flat glass industry on its own can define, but we need the impact of other industries, the plastic and rubber, the woodworking, and all others that were involved and did an excellent job. Together with Wolfgang, we learned how important the ISA 95 is. Honestly speaking, for me, it was not known to that detail until this respect. And we added also the job feedback. I'll come back later. Certainly, when you put in all this information and requirements from the different domains, the model cannot be the same, but it was specified in the 40001/3. And it was a little bit extended. The big advantage was it is not completely different from the model that we had previously. It's to 90%, it's more detailed to a degree that maybe not. But the important thing for us, or the important learning for us, was that now we can use this as a basis, which is a very global basis, and where we can be sure that this will stay for a long time, as a lot of companies, not only in the flat glass industry, will apply this standard. And we just have to put our add-ons into the flat glass specification. And that means that we really have a strong reduction in the volume of our own specification. So it means that from coming out of a situation where we said, let's find something to unify the flat glass industry and create a standard. And yes, we are so particular, we cannot be compared to anyone else. We have changed into an organization which says, hey, look what's already there on the machinery. For instance, for the file transfer, for the feedback, etc. And only particular things like the job target definition and some particular specifications and conventions that had to be applied, had to be agreed, they shall be then in the specification, meaning that the new specification that is going to be released is of scope, of intellectual scope that is required to be recognized, is less than 1/3 of what we had before. And I think that's very important, because nobody's very interested in reading a lot of pages and saying, hey, I think I have this already somewhere else, and why do they make it in this particular way? But having said that, I don't want to focus alone on saying, okay, look, we reduced the volume and scope of our own specification, and therefore maybe it's not worth that the flat glass group may sustain in the future. On the contrary, I think what we managed to do is to change our way of thinking, of saying we go beyond being self-sufficient. And what I mean with going beyond being self-sufficient is simply by asking questions within the group that we relied on later on into the machinery. And I'd like to show this on 2 examples. The first one that we had when we were talking about machine feedback was, can we calculate OEE or availability as a base for the OEE only on machine information? And if you talk to machinery builders, especially if they do Industry 4.0 machines, they say, yes, for sure we can do. And I agree, they can do it. But is it the proper way to do it? And how can we do it together with OPC UA? And that were the questions that we were asking ourselves. So we started first to investigate, okay, which basis can we use for this specification? And certainly, we went off the idea of creating our own formalism for that and tried to use what was already existing at that time, meaning a kind of an understanding, a definition of how a machine can display its actual state of working by using of a state, which can be out of service, not executing, as explained here on the left-hand side, and an application mode, which can be processing, maintenance, setup, and so forth. So this was already well established, and we thought, do we need something in addition to create OEE? Yes, in the beginning we thought we need, but in the end we found out, no, it's purely sufficient. You just have to be smart. And what I mean with being smart is what I'd like to explain here in this small slide. In this small slide, what you see is a machinery with its downtimes and working times. So you see it was 1 hour out of service, 2 hours not executing, and 5 hours it was executing. If you leave now to the machine without being connected to an MES or ERP system and getting smart information, provided that, then the machine would consider, hey, we had about 8 hours in total. We were working, we should work, and we were only working for 5 hours. And that gives me an availability of 62.5%. I hope you all agree to that. You can do the maths on your own. But the question is this true? Yes, if you calculate it like that, and if you say that is the standard how it's calculated, then it's fine. But is it agreed, and is it an international standard? And I'd like to show you why you should put such simple answers into question by a very simple approach. Let's suppose you have an MES system, and in this MES system, you have planned already 1 hour of planned downtime for maintenance on your machine. So that changes completely, because in that case, you're not counting on 8 hours, you're counting on 7 hours, and suddenly your availability increases from 62 to 71%. And the beauty of that is that suddenly you are compliant with international standards. So that means, and I hope this is very clear, is that the machine as on its own can be a source of information, but can never be self-sufficient without getting information from an MES system in order to calculate the proper values. Now, having said that, it's not a piece of cake to calculate the right values. And this is why I'd like to show you a little bit what is behind the ISO 22400. The ISO 22400 example given for the times has a defined model. And honestly speaking, I find it very beautiful because it's simple. It talks first about planning. So you have a reference time that can be your 8 hours of production or whatever you have, or a day shift of 24, right? Then you have the possibility to say, look, from this time I take only operation time, and if there is a planned downtime, then I have a planned busy time of only about 6 hours, whatever it is. But the point is that as a second source of information, it takes already the machine also with the times of actual unit busy time, processing time, and actual production time. And if you use this nomenclature in order to calculate, then you are on the right track. But the point is, how can we bring them all together? And this is where we did a great job providing information from our OPC UA model and combining it together with information from MES. And here we had the great help of one of the experts developing the ISO 22400, where we made a reference table how we could incorporate the states of the machine itself into this model in order to calculate the proper KPI factors for the OE. And the beauty of it is that this is now part of the standard of the 40001. I think it's the 1 or the 2, whatever, one of these specifications. Important is here we could show that the glass industry itself was no longer thinking only on its own. It started an idea, and it brought it to the attention of the machinery. And even further, we thought of what can be a reasonable business case that can be achieved by integrating other standards. And in the same way, we were thinking about job feedback. Now, what does job feedback mean? A regular flow of job is exactly presented in the graph as you can see it here. You have the job definition, you prepare it, you run it, and you end it. It can be interrupted, aborted, whatever. However, whatever the job is, may it be a milling and drilling, may it be a grinding of the surface, may it be a drilling of a hole, may it be a painting, may it be an assembly of an IG line. Honestly speaking, it doesn't matter. In the end, what you have is general information, which means when was the job done. Product information, that means which forces, which positions, which tools were used in order to produce the material. And the third is the bill of material, becoming more and more of importance as we have now to track supply chains in order to go beyond let's say, in line with upcoming regulations about supply chain management and supply chain follow-up. So we have created also on our own model for glass and even for another industry in order to show how such a standard of communication can look like. And the beauty was that Mr. Manke, Wolfgang, he came across and the ESA, and he saw that without knowing from our side, he saw that basically the standard of ESA 95 is not so far. So we could basically compile both informations and we could create a model for job feedback with this universal. And I show it just for you on two examples here. One is a cutting of a glass where out of one product, that means one big glass sheet, as mentioned by Gesine, 6 meters by 3 meter 21. The few sheets, like 5 of the A1 and about 6 of B2 and a little bit of waste, is created out of it by cutting and by scoring and breaking, basically. So it allows to do this kind of operation, as well as exactly the opposite, that you assemble something. You have sources of raw material that can be paints or that can be spacer, desiccant, and gas, and you compile it to a product, including also general information and including also process parameters through the way. And the beauty of that was, once again, we started in our group, we brought it to the attention, and we could create a standard that is broader than what we will ever have in the flat glass industry. And the broader a standard is, the more people are potentially applying a standard, the more it has the chance to survive for the future. And that was the interest that we had. So in total, if you resume, I like to resume what was been told in the last 15 minutes. Basically, we came from a state where we said, okay, let's find something to be self-sufficient, into a broadening of the mind, saying, look, if you put it on broader basis for the machinery, it can be universal, and honestly speaking, our machines are particular, but in the end, they are machines. To a third point where we say, let's try also to expand and look into other standards in order to create really value for the business, as we did it for the OKPI standards, as we do it also for the job feedback, in order to fulfill future and upcoming standards. And with these words, I'm very happy, and I was very happy to hand over my appointment to the chairman, to Gerald Fehringer, and he will give you now the details about the job target definition. That means the real details that are conveyed in our model. Thank you.
All right. Thank you, Markus, for introducing us to the companion specification and how we see it being used. I will continue now with the so-called job target definition for the glass industry, which is something that we have in the release phase at the moment as the VDMA standard sheet 24124. The job target is basically a result of the many discussions we had on the job management in the end, because we found, or we knew there was a lot of complexity sitting behind of it because of the product complexity that Gesine explained, because of the many different processing steps that we have and the many different kinds of machines that are being used here. And we finally came up with a structure that is depicted here. We said, okay, on the input as well as on the output side, we basically need the three main building blocks, which are the products, of course. I mean, on the input side, products arrive at the machine, and these products need to be described through a bill of material with shape information, geometry, and the processings that they already might have at this point. And as well as on the output side, we might have one or more products that are the result or what are exiting the machine at this point. And again, they need to be described with the details of material, bill of material shapes and processings. Then there are certain machines where we need additionally some layout information. Like Gesine has explained, the cutting process, for example, is one where layout is something very important, because the production planning system is generating an optimization, trying to utilize the larger stock sheets as good as possible to reduce the waste, and this layout information needs to be transferred onto the machine. And then we have another building block, which is the storage, because let's say transporting or for the transport of the products between machines. Very often racks or hard cars are being used, and the storage structure allows us to describe how the products are being stacked on such storages, for example. Coming to a bit more detail here, bill of material is something where we have a general mapping onto material types which are defined within our group and which are defined within this VDMA standard sheet. And these materials can be, aligned to each other using transformation information. That means if we have an IG unit or any other laminated unit, for example, then we need to assemble multiple sheets of glass with some other materials sitting in between, and we need to locate these materials with reference to each other, and the transformation allows us to do this. And we have another concept, which is the instance, which can refer to different types of materials or even processings, and that allows us to assign identification barcodes, for example, to the material, so that this can assist the scanning process, for example, on a machine or at a machine. A second very important building block for the data structure is the shape. Of course, our products have a shape, have an outline geometry, which we define through geometry paths, and these paths being combined as lines and arcs. We feel that lines and arcs are sufficient at the moment to describe any of the outlines that we meet in the glass industry at the moment. And this describes not only a product, but it can also describe, for example, the shape of a processing like a cutout, or the shape of an area on the glass surface that, for example, needs to be screen printed or sandblasted or whatsoever. And then, of course, a very major building block is the processing itself, because also, like Gesine has already indicated a bit, there is a wide range of processings that need to be done. And we already have a catalog of around 35 processing categories being mentioned in our standard sheet. And I guess we still have around the same number ahead of us to complete. This will be then integrated in future versions of the standard sheet. And again, we are using of the same transformation logic to then locate these processings inside of the geometry of the materials or of the product. If you look at the sketch that you see on the right-hand side, you see drill holes. And of course, these drill holes need to be done in a very precise location, and the transformation allows us to actually locate this precisely. The other thing is that the processing structure itself is done with a recursive definition. That means it can hold sub-processings, like, for example, a cutout requires a drill hole as a helper process to first of all drill the hole that allows then the tool to move in to finally mill this cutout, and to indicate that there is a group of processings that belong together, where, of course, one is playing the major role. We said, okay, this can be done through recursive definition. Then coming to another major building block, and that is the layout information. This, like I said, is for example used for glass cutting machines, but also for layer cutting machines. It's essential. And also, if you look at the tempering furnace that has a furnace bed, and the furnace bed needs to be utilized with multiple sheets of glass being stacked onto it or placed onto it, we need the production planning system to do the optimization for it, and we need to transfer the geometry or the layout information here. We do this through rectangles, and again, the rectangles have a recursive logic in it. That means inside of a rectangle, we can have more rectangles, or we split the one rectangle area into multiple sub-rectangles, which again can have sub-rectangles and so on. That means we have a kind of endless nesting capability through it, and this allows us to really, serve the purpose of cutting on a cutting table, which is very special. And then the third, if you remember the job target definition, one of the major building blocks per input-output is the storage definition. And here we were choosing a cuboid as the basis. That means a rack or something like that is a larger cuboid, which can be split into smaller cuboids, which are, for example, the sides. If you look at the right bottom image of a rack, you see two sides, which are two cuboids. And inside of these two sides, we have then stacks, which are again cuboids. And inside of the stacks, we can then have, we call it virtual slots, in which then the final products are located. And this allows us, again, to very flexibly define or describe how material and products are located on certain storages. And typically in the glass industry, of course, we use L-racks or A-racks or hub cars, like already indicated, and this can be very well modeled through such a storage structure. And finally, the job target definition itself is something recursive. That means it can hold sub or inner job target definitions. That means if you look at that rack that is sitting there in the middle bottom area, if you consider this as a job that we transmit or transfer onto a robot, for example, then the job for the robot is to then unload every piece of this from this rack and load it onto some machine. And of course, the robot has to do it in sequence and all of these sheets in a row. And then only this rack gets replaced with possibly another rack. And then the robot, the rack is the job that he has to do or to perform. And then it has inner jobs for the individual pieces of glass that sit there on the rack and that need to then have some processing to be done on the actual machine. Then I would like to highlight also another, let's say, piece of property that sits there in the definition. And this is the realization mode. This realization mode is a property which we can have, or we will have, or we have on a material level, as well as on a processing level. And the realization mode can basically have three states. The one is the input state. That means through this we indicate the material or the processing are already there on the inlet. That means the material is already there, or the processing has been applied already on a previous machine. That means this is nothing to be done on the current machine. If we declare a material or processing to be output, then this means we want to add this material in this at this processing step, or we want to actually execute this processing on the current machine. And if we define it as future, then this means it's not there in the inlet. We are also not supposed to do it on the current machine. This is something that will be coming up in the future in the lifetime of this product. And what's the advantage of this? The thing is that we can transfer the full product complexity and the full product information to each and every machine, actually. And with declaring some items or some processings or some materials as the output, we indicate, okay, this is the part you actually need to do. And if the machine is intelligent enough, or maybe in the future becomes intelligent enough to also consider what comes along in the input or what will be there in the future output, it could consider. As an example, if you, for example, have a scanning device in front of the machine, which is also coupled to the machine, then it might be able to check whether these processings are really done. Because, for example, if you temper the glass and then afterwards you would like to drill a missing hole, this is rather not possible. You really have to scrap that piece of glass and need to start from the beginning. But if you have a scanning device which could check, are the previous processings done, then the machine becomes more intelligent in that sense and more fail-safe for the production flow. Or if we look at a tempering furnace, for example, the tempering furnace, like Gesine explained, we apply heat and cool the product then down again. And on the tempering furnace, it is very essential that they know about what processings have been applied early on already. If you look at the example here in the bottom, there's a typical door, and the door has some drill holes, as you can see. It has some cutouts in the bottom or even in the corners. And it might have a coated surface, and some parts of the coating might have been decoated. That means being removed from the surface. And if the tempering furnace now applies the heat uniformly, this would cause possibly waviness of the sheet, of the glass sheet. And this is something that should get avoided, because later on, if we then would like to assemble two such sheets, then ideally they should be flat, no waviness, to really adhere together. And this is a kind of intelligence that the tempering furnace can apply then, knowing that on the input side already certain processings have been done. And even if in the future a new machine comes along and we transfer all the information already, then that machine might pick up that information and apply certain special recipes or whatsoever. So this is an important step, I think, or I believe, that we did here to really being able to pass on the full information of the product at every stage, basically. And then finally, coming to a bit of technical definition here, we are using a JSON representation of this model, because we feel this is a very common approach and can easily be handled with many programming languages. And we are making use of protocol buffer definition language. Possibly a few of you might be aware of that. And for this definition language, there is interpreters or precompilers that allow automatic code generation of classes and methods, so that it becomes rather easy, for example, to fill such a model, to serialize it as a JSON, or to deserialize it from JSON into an internal model, which should make the handling of such kind of information rather easy for whoever is trying to apply these concepts. Yeah, I hope I could give a rather comprehensive overview of our job target definition with it, and what makes up the complexity, but also the beauty of it. With this, also in the name of Gesine and Markus, I would like to say thank you for your attention, and will now hand over to Heiko to assist with the Q&A session. Thank you.